Okay, now we have Jesse Daas from Radboud University, and he's going to tell us about quantum gravity and the Event Horizon Telescope.
Yeah, hello everyone. Thank you for the introduction. Yes, I'm going to be talking about macroscopic, microscopic events, and of course, effects, sorry. And of course, we all know where the microscopic comes from. That comes from our quantum gravity theory. However, the difficulty in obtaining satisfactory theories is that we cannot confront them with experiments, because every time we try to do so, these effects are really, really small, and we don't have access to, at least in the regions where we have access to them observationally or experimentally. And what I'm going to be talking about is a mechanism which might make these microscopic effects very big, such that they lead to observable macroscopic consequences. So this picture you've all probably seen. It's a picture made by the Event Horizon Telescope of the M87 Black Hole. And the two things in this picture that are important. First, it's a supermassive black hole, so it's not of Planck mass, its mass is huge. And second, there's a shadow in the middle. And the shadow, or brightness depression, is a consequence of general relativity. It's largely independent of astrophysical details that are not so much of interest to us. So if you have an event horizon, then it is the photon radius which determines the size and shape of the shadow. Okay, so what we want to do is study black holes or compact objects from the viewpoint of quadratic gravity. And the reason I want to do this is because, well, clearly for these supermassive black holes, we are in the classical regime, and we want to investigate what happens if we deviate from GR. And the reason I pick quadratic gravity, there's quite a bunch of motivation for it, but for me, the most important reason is that several quantum gravity theories predict the presence of these terms, quadratic and curvature, in the action as a low energy correction. And the terms that are quadratic are naturally expected to be the ones that will have the biggest impact. Okay, so just summarize, the motivation is quantum, but the treatment will be classical, purely analogous to GR. So then we want to find solutions that are spherically symmetric, and these solutions, I'm not going to talk about how we get them, but they depend on 5 parameters. So there's the alpha and beta, which are the coefficients that appear in the action, like Newton's constant, and there are 2 additional parameters, S0 and S2, which characterize the compact object itself, like its mass. Then the solution that we obtain, if we pick M to be 10 times the Planck mass, so this is not a supermassive black hole, this is Planck-sized stuff. Here we can expect wild things to happen, and we obtain solutions that are of 2 types, either naked singularity solutions or wormhole solutions. So 2 things to take away from this plot. First, notice that the solutions far away from the would-be horizon follow Schwarzschild very closely, and then either the function f shoots up or shoots down. If it shoots up, it's a naked singularity solution. If it shoots down, it's a wormhole. Okay, graphically it looks like this. And of course, the naked singularity solutions are the ones of interest to the EHT because they have a very good chance of being ruled out by the observations, because the shadow might disappear in this case. So of course, we are in the astrophysical regime, as I said, and there the mass is much higher than 10 Planck masses. It's really high. This has the downside of that we can no longer numerically integrate, because this mass is just, it's 10 to the power 50 Planck masses, so it becomes impossible to do this. There's a small upside. We do have analytic control over the solution far away from the black hole, and at R equal 3m is far enough. So this is the photon radius. Here we can linearize the system, and we have analytic control. And so we can actually calculate what the shadow size will be if you do this, choosing very natural Planck-sized values for our parameters. And if you do this, you get a typical deviation parameter of your shadow, which is 2 times the exponent of -6 times 10 to the power 50. Yeah, that's really, really small. And the thing that I want to talk about, the topic, is to make a potential really wild claim, and that's that corrections of this size are actually enough to prevent the event horizon from being formed. So this is what I'm going to talk about now. And the way this happens is through a mechanism that I call the blow-up mechanism. And to understand this mechanism, it helps to think like a numerical integrator. So we cannot numerically integrate, but we can still think like one. How does a numerical integrator think? Well, first you need to provide an initial condition. This is just a small perturbation around the Schwarzschild. I don't think I have to convince you that it's small. And if your function f is of this form, what do you do then? Well, then you solve for the highest order derivative in your equation of motion. This happens to be the third derivative. And unsurprisingly, what you get is you get the third derivative of the Schwarzschild plus some tiny correction, a correction that's small. Then what you do, you update your lower derivative functions, right? You increase integration time, or you decrease r, because we integrate from outside to inside, and you repeat. You go through this. Where does this blow-up mechanism kick in? It kicks in at this tiny correction over here. Because if you look more closely to what this looks like, it looks like this. So a tiny factor, something that's still very small, exponentially suppressed, times this 1 over r minus 2m to the power 4. And of course, if you are at r equals to 3m, this prefactor is meaningless. But as you come closer and closer to r equal to 2m, then of course this is a pole, and it starts to become bigger and bigger and bigger. And so the situation that you're now in is that as long as 1 holds, that you are close to Schwarzschild, then 2 must hold as well. And so if you start out close to Schwarzschild, meaning yes, your solution is asymptotically flat, then you will always get your cube derivative to be of this form. And so you will remain in this situation. You cannot escape it. It's forced by the equation of motion, which the solution has to satisfy. And you will always, you would just always decrease r, staying close to Schwarzschild, as long as this term is small, which it will be because it's exponentially suppressed. But of course, when you hit this r equals to 2m, you will never hit it, but when you get close to it, this prefactor becomes bigger and bigger and bigger, and at some point, this second term will actually start to become significantly large to really impact the solution that solves your equation of motion. So one thing I want to emphasize is that you never hit this pole. It's not like this is unphysical or something, because before you hit it, this thing is large, and that means you will deviate from Schwarzschild, and that means this is no longer true, and that means this is no longer true. So you don't hit it. The point is that as long as you are in this situation, this gets the chance to make these quantum gravity of quadratic gravity contributions dominant. So is this really what's happening here? To help convince you and myself more, we can actually make a prediction. So if the sign of this tiny factor is positive, then your function, as you integrate from outside to inside, goes down, and that means it will go to 0 faster, meaning we get a wormhole solution. If it's negative, then you will, instead of going to 0, you will go away from 0, and so you get a negative gravity solution. And we have actually analytic control over this tiny factor outside of the would-be event horizon, because these solutions are these corrections are still so small that this linearization still holds. And so we can now make a prediction of the sign of tiny factor, and based on the parameters that classify our solution. And the nice thing is that for our Planck-sized system, so m equals to 10 masses, the flow mechanism is also at work, because here this e to the power minus 2m, so the corrections at the horizon are of order 10 to the power minus 9, so still incredibly small. And so now we have all these numerical solutions that can form as a test bed for testing if this mechanism is really at work here or not. So just because so we're all on the same page, green means good, red means bad. And now let's compare to the numerical solutions that we have. So I just take a slice of the phase space. I didn't talk in detail about the parameters because I don't have time for that. But we just take a slice of the parameters of the phase space, and each of these squares the signal whether it's a naked singularity solution or a wormhole solution. And then we compare to what's the sign of this tiny factor predicted by this blow-up mechanism. And we get a 100% match here. Of course, life is never this perfect. So if we take another slice of the phase space, then there are some red squares in there. Luckily, we know very well why these, how this comes, what's happening here. And here, I don't have too much time to explain, but what's happening here is that this tiny factor, which is also a function of r, just switches sign right outside the would-be event horizon. And so there's an ambiguity, should I read off the sign just before or after it's passed through 0? And so there you cannot really make a good prediction. Overall, we tested of order 1,000 solutions, and 98.5% were correct. And of all the other ones, you had this similar feature that this tiny factor crosses 0. The nice thing is that for large masses, the larger your mass becomes, this problem will just go away. And so what's the upshot? And this is the wishful thinking slide, if you want. If you can then rule out these naked singularities, we have good motivation that you can, then you can rule out the parameters for this tiny factor if you assume m to be really small, for which this combination is less than 0. And if you can still rule out the naked singularity solutions that you would get even if m becomes the size of the mass of M87, well then, if lots of ifs, this needs a lot more rigorous motivation, but then you could perhaps eventually rule out Planck-sized quantum gravity-induced parameters based on this mechanism that allows these small corrections to become big. Of course, there's a lot of questions to follow up. How rigorous is this? What about stability? If these tiny corrections can have such a big impact on the solution, are your solutions stable anyhow? Can you really rule out these naked singularities just because there might not be an event horizon, but there is still enormous amount of redshift? And how general is this blow-up mechanism? So it's not limited to quadratic gravity, it's also present in other systems. And how general is a question that I still have. But I am convinced that this is quite, at least to me, an interesting that I think deserves attention to be worked out. So, thank you.
Yep.
I don't know if okay. Yeah, I have a question. I am wondering how much depends this blow-up mechanism in your choice of coordinates? Because if I was, how do you call it, an integrator, I would make a change of coordinates to Eddington-Filkenstein coordinates first.
Yes.
So because everything look a bit like depending on the coordinates, right? That you have a coordinate singularity there. And but I have another question. Well,
okay. Okay, sure. So I get this question. I have the same thing. So first item on our to-do list is to make a change of coordinates, see if it's still there. I do want to emphasize that there really is not a horizon in the sense that light rays can really escape. So we checked this with the geodesic equation. So it really seems like there's no horizon if in the solutions that we have. And it's not like, again, as I said, that this is unphysical or a real pole, because this is only true if your solution is close to Schwarzschild, which it won't be. That's the statement. But yes, I completely understand your question, and we want to investigate this further. Yes.
I was also, can I make another question? Yeah, I was also wondering, well, this is a bit more, I don't know, connected to observations, because you want to connect to the Einstein, to the Event Horizon Telescope, that I guess they are not really testing the horizon. Like the best they can observe is the photon ring, and that's still far from the horizon concerning quantum gravity. So
so it's a little bit subtle. So it's the photon ring that determines the size and shape of the shadow, but only if it's there. So the reason that the shadow is there is also because of the event horizon. Not necessarily so, but in general relativity, we have an event horizon and we also have a shadow because of it. So there are alternative solutions, other systems that do not possess an event horizon that still might possess a shadow. That's certainly a possibility. So it's not like the HT 101 necessarily confirms the existence of an event horizon, but for quite a bunch of naked singularity solutions, for instance, the shadow disappears. And so this is actually assuming a very simple accretion disk or sphere, I should say. This very tiny black dot here that's now the shadow, whereas it would be this size if you had the event horizon there. And so, and then the second thing is that now that of course you have matter that can fall in to the would-be event horizon, which in GR would have no impact on the image because it can no longer emit light, but in this case it can, and this matter builds up here and becomes incredibly hot and dense, such that it can leave an observable imprint, which can help fade this brightness depression. So it's a subtle discussion, but it's not that necessarily no event horizon means no shadow. That's definitely not true, but it still might be ruled out. Sorry?
That could happen also that even with a horizon, the redshift could be so high that we don't get that light.
Yes.
Because of the redshift.
Yeah, exactly. So then it becomes a question of how far does this matter extend away from this event horizon, which it will do at least a little bit more because of the high pressure that's created. And then is it enough is this huge amount of light from this huge temperature enough to compensate for this redshift or not? So, yeah.
Okay, let's thank Jesse.